All right. The last thing we can talk about is kind of the transformations of these graphs. So first we'll talk about transformations of tangent and cotangent, and then later secant and cosecant. And this might seem new, but actually it uses the exact same properties that we saw before. So the same thing for like exponential functions and log functions that we saw unit 1, and also the translations of sine and cosine that we saw just a couple objectives ago. So like y equals 2 tangent x. Well, what would this have done if it equals y equals 2 sine x? Let's just kind of remember that one. That would have changed my amplitude. That would have stretched it vertically. And so just like before, this one is going to stretch vertically by 2. Right? So if I just kind of quickly sketch in what my tangent graph looks like, and I remember that it goes through here and then repeats a couple of times. This is a super rough sketch, but this is all we need for this. If I stretch this vertically by 2, that means that all my y values are going to get twice as big. So instead of going like this, we're going to go more like that, and like that, and more like that. It's not perfect, but this is a decent idea. My y values are getting twice as big. So we took our original tangent graph, stretched it vertically by 2. Right? My negative tangent x, well, a negative in front of my function is always going to reflect it over the x-axis. So again, if I start with my tangent sketch, which is something like this, then my graph that I'm looking for here, I'm going to flip this over the x-axis, and it's going to look more like this. I don't think my original sketch wasn't perfect, but it would be something like this. And this is really all I'm looking for when I say sketch these things. I don't need it to be perfect, but I want you to be able to expect what the graph would look like, so that if you use your graphing calculator, you would say, hold on, I think something's wrong here. If you like typed it in wrong, I need you to recognize when you might be making a mistake. Let's talk a little bit about a little bit more how to graph these, especially if we might change the period of these. So both of these maybe change things with my y-axis, but didn't change anything on my x-axis. We can also change some of our period here. And we would do that just like we did before for sines and cosines. To change my period, it's going to be by multiplying something with my x. So when there's a multiplicative factor in front of my x value. Okay. So if I ever ask you to graph just like one period of one of these, and maybe that my period has changed a little bit. Well, let's just remember my base tangent graph looks something like this, and it went from negative pi halves to pi halves. That was kind of one period of it, and then reflects to the left and the right, right? There's more copies of these to the left and the right. And so if I change my period a little bit, we might want to graph it from like maybe negative pi over 2k to pi over 2k. So instead of negative pi over 2 to pi over 2, we're going to kind of stretch it in or out one way or the other. But my regular cotangent graph kind of started like this. If I'm going to do a sketch over one period, I want to be able to do like one continuous period kind of between my vertical asymptotes there, between those bars. And so normally we might do from 0 to pi for just the graph of one period of cotangent. And so if I mess with this a little bit, instead of 0 to pi, I might go 0 to pi over k. Okay, so we'll use that here in a little bit. So here I want to find the period and describe how to get there from the original one, and then maybe we'll sketch this a little bit too. So y equals tangent to x. That's going to change my period, right? And oh, I didn't fill in a blank here. These, if you put in a k in here, the period is going to change by a factor of k. So it's going to be pi over k as my new period. And so if my k is big, it's actually going to be a shorter period. And if my k is small, then this is going to be a larger period. So if I have that 2 there, then my new period is going to be pi over 2 instead of just pi. It'll be pi over 2. Okay, and I might want to look at this over the interval negative pi over 4 to pi over 4, which is an interval of length pi over 2, because if I take a pi fourth and a pi fourth, you take a fourth and a fourth, you add them together, you get a half. So if I do a pi fourth and a pi fourth added together, I get a pi halves. So I might look at it over this interval. And what this period is going to do, this 2 is going to compress horizontally by a factor of 2. It's going to shrink it, right? So my normal tangent looks like this. I'll just graph one period. This is what normal tangent looks like. I'm going to compress this horizontally, and so my vertical asymptotes are going to be there at negative pi over 2 and pi over 2. My graph's going to look more like this. It's going to be squeezed in. So you can't see me, my video is off, but what I'd like to think about is I'm putting my left hand and my right hand out, and I'm like thinking about squishing this graph in. So if it were in front of you, how would you squeeze it? Okay, another thing that I like to think about when we have these period translations is it's kind of weird that when we have a 2 here, it actually gets skinnier. But for the period translations, I like to think about, like, if you were to watch a movie on double speed, would it take longer or less time to watch it? If you watched a movie on 2x speed, well, it would take half as long to watch it, right? So if I have a period of 2, or if my function has 2x in it, then it actually takes half the distance for that to happen. And this is the same, this rule works for all of our functions that have a period change. But if we watch it on 2x, then it's going to take half the time. So my period then is half of what it used to be. Okay. All right, this next one here is very similar. We have y equals tangent of 2x minus pi over 4. So we still have a compressed horizontally by a factor of 2. But we also have another thing going on. We also have this pi over 4, because that is subtraction immediately from my x. That's going to be and shift right pi over 4. It's going to be a right shift, first off, it's going to be left or right shift because it's by the x. It's going to be a horizontal shift. And then it's going to be to the right because it's a minus, and x is always the opposite of what you want it to be. We'll skip the graph of this, but hopefully you can kind of visualize what that would look like. And then you could open up something like Desmos to see what this actually does look like. And you should be able to confirm what you're kind of thinking or imagining in your brain. Okay. All right, secant and cosecant, we tend to kind of keep it over the same interval we might be doing for sine or cosine. So sine and cosine have period 2 pi, right? And so this is going to have period 2 pi over k, however what I'm scaling it by. And so we're going to probably look over the interval 0 to 2 pi over k. Just, it's actually kind of the same thing of starting at 0 for sine and cosine and going outward. Okay, so let's have a couple more examples. So what's going on here? I have y equals 1/2 cosecant x. Well, that 1/2, it's out in front. So this is not going to be a horizontal stretch or compression. It's going to be a vertical compression. And I know it's going to be a compression. It's going to shrink it down because that number 1/2 is less than 1. So we're going to compress or vertically by 1/2, right? So cosecant normally looks something like this. Not perfect, right? And you can always go double check. What did cosecant look like? Oh, I did it wrong. Dang it. Why did I do it wrong? Let's start over. Cosecant is 1 over sine. Oh, I was thinking about the zeros, not the ones. Okay, so I sometimes like to start with a sketch of sine to remember. And that tells me, oh, that's where cosecant is going to have its mins and maxes. So I'm going to erase those. And remember that cosecant is going to look like this one. It's going to have its mins and maxes at the same places where sine and cosine has its mins and maxes. Okay, and I'm going to compress this vertically by 2. So my new graph, instead of coming to 1, is really going to come to 1/2. So they'll come up a little bit higher. So it might look something like this. And these are sketches, so it's hard to tell, but it should be up a little bit higher. And this is one that really, to see the difference, go to Desmos and graph both cosecant of x and then 1/2 cosecant of x and see what's going on there. So let's try out here. In red, I have my cosecant graph, and it does have a y value of 1 there at my mins and maxes. And so my cosecant one is going to have a y value only of like 1/2 or -1/2 at the mins and maxes. So let's see what that looks like. Okay, cool. So just like we were saying, we now have a y value of 0.5, and all of these y values as we go along are going to be half as small as the ones right above it. So that is our vertical compression by a factor of 1/2. All right, in this last example, we actually have a lot going on here. And before we dive into it, I need to think about how I have this kind of 2x plus pi over 4 there. And we saw this in our sines and cosines, that to really see what's going on, I need to like factor my 2 out to be able to see what kind of left or right shift I have going on. So if I factor this 2, I pull an x out. And it's maybe hard to think about factoring out a 2 from pi over 4, but really what we're doing is we're doing pi over 4 divided by 2, and that's like the number that's going to go right here. That's pi over 4 times 1/2, because if I am dividing, the same thing as multiplying by the reciprocal. So that's really pi over 8. And I can check myself that if I distribute this across, I would get 2x, which is what I started with, and 2 times pi over 8, and that'll reduce to pi over 4. And I do need to really factor this out like that before I kind of decide what's going on. Now I can read each piece, and I see that this one is going to give me a vertical compression by 1/2, just like the previous one did. This is going to change my period. This is going to be a horizontal shrink. And this is going to be a shift. It'll be horizontal because it's plus or minus, and it's going to be to the left by pi over 8. So I would take my cosecant graph and I would shrink it horizontally by a factor of 2. Vertically compress it by 1/2 and then shift it over to the right pi over 8. I might also want to talk about what is my period here. Well, the formula here is that I take my 2 pi and I divide it by my k, which in this case is 2. So 2 pi over 2. So it's going to take only pi for this to happen because I'm shrinking it horizontally by a factor of 2. Everything's going to happen twice as fast.